Welcome back to another lesson in MCV4U. Today we'll be looking at a review of sketching polynomial and rational functions. So let's look at this polynomial function here, and it says graph y is equal to x to the power of 4 minus 2x cubed plus 2x minus 1. And here, when we look at this question here, some of you might choose to use factor theorem. But here, we can simply also just factor by grouping. And here, I'll just highlight the negative 2x cubed plus 2x here. And so if we factor by grouping, we can rewrite this as y is equal to x to the power of 4 minus 1 minus 2x cubed plus 2x. And here, if we rewrite this, we can also factor out a negative 2x cubed from the last two terms. So here we have x to the power of 4 minus 1 minus 2x, and we're left with x squared minus 1. Here we notice again that x to the power of 4 minus 1 is difference of cubes, and so we can rewrite this as x squared minus 1 and x squared plus 1, and we're left with negative 2x x squared minus 1. Here we see that we can factor out a common factor of x squared minus 1. So if we factor out x squared minus 1, what we'll have left over is x squared plus 1 minus 2x. Here, if we move the 1 to the end, and we write it as x squared minus 2x plus 1, we'll notice that this is a perfect square trinomial. So here, we notice that that's a perfect square trinomial, and the x squared minus 1 is a difference of squares. Again, so we can rewrite this as x minus 1, x plus 1, and here we would have x minus 1 squared. Here we see that we have x minus 1 here and x minus 1 squared, so we can combine that to be equal to x minus 1 cubed, and we also have x plus 1. Here we see that if we look at our x-intercepts, two x-intercepts here. So again, x is equal to 1 and x is equal to negative 1. And here our y-intercept. So those are our x-intercepts. And our y-intercept here, and when x is equal to 0, will be equal to negative 1. Okay, so we know that we have our x-intercepts at, again, 1 and negative 1, so we can draw that on the graph. We have, and then we have a y-intercept at negative 1 as well. And we'll just label our x and y-axis here. So there's a couple important things to understand here. Again, when we're looking at polynomial functions, the first is the order of roots. Second is the degree and leading coefficient. And then lastly is the end behavior. Here we know that the order of roots for 1 is at order 3. and -1 is order 1. The degree is 4, and we have a positive leading coefficient. And then that means the degree 4 with positive leading coefficient, our end behavior, we're going to start at quadrant 2 and end in quadrant 1. Here, when we look at our function, we'll start in quadrant 2. We'll pass through the x-intercept of -1, and then pass through our y-intercept of -1, and then it'll behave like a cubic function. And x is equal to 1, and then it will complete or finish to positive infinity and end in quadrant 1 as well. Okay, let's keep going here. So when we look at rational functions, so horizontal and oblique asymptotes in rational functions, consider the rational function with numerator of degree n and denominator of degree m. So here, it's a little hard to see, so I'll just rewrite this. So f of x is equal to a power of nx over b to the power of m x. And so here, we're looking at the exponents of n and m. And so if n is less than m, then we know that we have a horizontal asymptote at y is equal to 0. If n is equal to m, we know we have a horizontal asymptote at y is equal to a over b. And then finally, if n is greater than m, then we have horizontal asymptote that does not exist. Okay, let's take a look at this. So here we have an example. It says given g of x is equal to 3x minus 2 over 4x minus 1, sketch of the graph. So here we see that we have an n and m value that are the same. And so here we will know that we have a horizontal asymptote at 3 over 4. So now we have a horizontal asymptote at y is equal to 3 over 4. Our vertical asymptote, if we look at 4x minus 1, we see that we have a vertical asymptote at x is equal to 1 over 4. Again, because 4x minus 1 is equal to 0. X is equal to 1 over 4. And our x-intercept here, x-intercept again here means that again our numerator is equal to 0, and also when y is equal to 0. So therefore here we have 3x minus 2 is equal to 0, and x is equal to 2 over 3. Also have our y-intercept when x is equal to 0. And so that's 3 times 0 minus 2 over 4 times 0 minus 1, or -2 over -1, gives us an answer of y is equal to 2. So here, let's place the values that we know onto the graph. So here, we know that we have, again, a vertical asymptote at 1 over 4. So again, the asymptotes are represented by a dotted line. So here we have vertical asymptote at 1 over 4. We have a horizontal asymptote at 3 over 4. And we know that we have an x-intercept 2 over 3. So we have an x-intercept at 2 over 3. And we also know that we have a y-intercept at 2. We know that in the top left quadrant, that again, the function will have to pass through the y-intercept and then get close to the vertical asymptote. And then on the bottom right as well, we know here that it will have to pass through the x-intercept of 2 over 3 and then get close to the horizontal asymptote of 3 over 4. Over here, we can show that using an inequality. So in this inequality, we'll put the x-intercept of 2 over 3, and then also our vertical asymptote of 1 over 4. So here, we're going to see again where the function is positive and the function is negative, or above the x-axis and below the x-axis. So here, again, if we sub in a value that is less than 1 over 4, so here, example, we sub in a value of 0, we'll see that here we'll get the numerator that is negative and the denominator that is also negative. So when we sub that in, we see that here it will be positive or above the x-axis. If we sub in a value between 1 over 4 and 2 over 3, see that here the numerator will be negative. The denominator will be positive, and so here we see that between 1 over 4 and 2 over 3, it is negative. So here, if we graph the first two, so here we see that it's going to be positive, so it's above the x-axis. So here we will see, start from negative infinity, plus the y-intercept of 2, and then go to positive infinity as well. And then get close and close to x is equal to 1 over 4, but never touch the vertical asymptote. Here, we see that it's at 1 over 4 to 2 over 3, which is negative. It is negative, so below the x-axis, starts from again, negative infinity, we'll hit 2 over 3, and here we can see that again, it has to be close to 3 over 4, so we can understand that it would have to be positive or above the x-axis from everything that's greater than 2 over 3. But here, if we sub in something that's greater than 2 over 3, so we sub in, for example, value of 1, you see here that again, both of them, the numerator and the denominator were positive, so which means that here it is positive or above the x-axis. So we see after 2 over 3, it would again be above the x-axis, get close to 3 over 4, which is the horizontal asymptote, but not quite hit that as well. So let's look at this next example. It says for the function f of x is equal to x squared over x cubed plus x squared minus 2x, find all asymptotes and intercepts. It says determine if the graph crosses any of the asymptotes, sketch the function, express the behavior of the function at each asymptote. So here, if we rewrite this as f of x is equal to x squared. And here, we can factor out at the bottom of x cubed plus x squared minus 2x, we're going to factor out a common factor of x. Left with x squared plus x minus 2. Here we can cancel out one of the x from the numerator and one of the x from the denominator. So here we'll be left with f of x is equal to x over, and we can factor out x squared plus x minus 2 to be x plus 2 and x minus 1. So here we see that we have a whole at x is equal to 0. And so here if we sub in f of 0, we get 0 over 0 plus 2 and 0 plus 1. So here we see that we have a whole at x is equal to 0. We have our x-intercepts and y-intercepts. So here our x-intercept is x is equal to 0. Again, that's when y is equal to 0. Here we have our y-intercept when, again, when x is equal to 0. And we see that there y is also going to be equal to 0. And remember, we have a whole at 0, 0. We have two vertical asymptotes. So we have vertical asymptote at x is equal to -2 and x is equal to 1. And we have a horizontal asymptote at y is equal to 0. So if we put these in, again, we have two vertical asymptotes. X is equal to -2. Another vertical asymptote at x is equal to 1. And we also have a horizontal asymptote at y is equal to 0. So here, now we're going to look at our end behavior. And so for our end behavior, first thing we'll look at is we'll look at the horizontal asymptote. We'll look at when x approaches -infinity. And here, we'll also look at, again, when x approaches positive infinity. And here we can sub in for -infinity. We'll sub -1000. For positive infinity, we'll sub positive 1000. And we see here when we sub in x is equal to -1000, we'll get a value that is very, very close to 0, but it's slightly below. So here we'll indicate it as 0 negative for the y value. Then when we sub in positive 1000, we get a y value, and that's very close to 0. Here it's a little bit above, so we'll indicate that as 0 positive. So here we see that with our horizontal asymptote, You see that for a horizontal asymptote here, again, as x approaches negative infinity, y will be, again, below 0. So here we see, if we write that, so here we'll see that it goes below 0 here. And then when x approaches positive infinity, we see that it would be above 0. Okay, now let's look at our vertical asymptotes. So our vertical asymptotes at x is equal to 2 to start. So again, here we see that vertical asymptotes as x approaches -2 from the left. So here we want to see again from -2 to the left. So here if we subtract it by -0.01, we see here that the y value will trend towards negative infinity. Here the y value will trend towards negative infinity. If we have -2 from the right, we add 0.01, we see that the y value will trend towards positive infinity. So here, from the right, we see that it will trend towards positive infinity. And then our other vertical asymptote, x is equal to 1. So here, as x approaches 1 from the left, so if we subtract it by 0.01, we see that our y value will trend to negative infinity. And our x, as what approaches 1 from the right, so we'll add 0.01, we see here that y will approach positive infinity. So here we can see that as well. Again, as x approaches 1 from the left, goes to negative infinity, and x approaches 1 from the right, is positive infinity. And we see again here that we have a hole at 0, 0. So now we see how we can graph this. So the graph, again, will follow the end behavior. So again, as x approaches negative infinity, it's below 0. And then as it approaches the vertical asymptote at x is equal to -2, y it trends towards negative infinity. Then as x approaches -2 from the right, you see here that it starts at positive infinity, will pass through the hole, and then as x approaches 1 from the left, it will now go to negative infinity. And then as x approaches 1 from the right, starts at positive infinity, and then as x approaches positive infinity, y will be above 0. And so that's what our final graph will look like.